Hello everyone, we are back. Stat 100 lecture, and here we're going to finish off 8.2 and do a problem from 8.3. I didn't quite finish off 8.2 on the last one, but we're starting to get into numbers and calculations, so I thought I would separate that section from the previous section, which was conceptual, from this section, which is going to be about calculations. So let's take a look again at our prototypical diagram. We have a population with a mean mu. We have, via the central limit theorem, we know that the sample means are distributed normally, and that the mean of the sampling distribution is the same as the mean of the population. That's exactly how I drew this picture. And there's also a standard deviation of the sampling distribution, which we call the standard error. So that is this is really two things. This is our estimator, and it is our sampling distribution, this curve. Okay, so let's now summarize all that we know. We have all the pieces. If you think hard about it, we have all the pieces that are necessary to make this statement. I'm not going to go into details about a proof. That's not what this course is about, but I'm just going to summarize the important points. So suppose we have a population with a population mean, mu, and a population standard deviation, sigma. So population has mean mu and standard deviation sigma. And this is, of course, is a continuous context. Okay, so we want a unbiased estimator. For mu. Turns out that x bar, the sample mean, is the best unbiased estimator. So that is the theorem. We already know everything we need to prove it, but we're not going to go through with all the proof. Now, the standard error, according to the central limit theorem, the standard error of x bar is sigma over the square root of n. However, we do not know sigma. Just like we do not know mu, we do not know sigma. We would have to know the whole population, every number in the population, to know to know sigma exactly. We do not know that. It turns out that we can do a reasonable approximation of sigma with S. So S is our sample standard deviation, and sigma is the population standard deviation. S is a reasonable drop-in replacement for sigma. So that is our standard error. Is also, we use the same word for both things, even though they're not exactly equal. I will call this S divided by the square root of n. I will call that the standard error. And that's what we use to calculate the standard error. Now, the margin of error, corresponding to 95% confidence, 95% confidence level, margin of error is plus or minus 1.96 times SE. Plus or minus just means it could be the actual value of the population mean could be greater than or less than our estimator. And the 1.96 we've discussed earlier. 1.96 is associated with 2 standard deviations. Sorry, it's not 2 standard, it's less than two standard deviations, but it's associated with the 95% confidence. And 95% is not a magic number. It doesn't come from the mathematics. It comes from tradition. So that is what we usually take to be appropriate confidence. A level of confidence is 95% confidence. That's not universal, as I mentioned before, but it's quite common. So that's going to be our main go-to for confidence. All right. So summary: X bar is the point estimator for mu. The standard deviation of the sampling distribution, or in other words, the standard error, is approximately S over the square root of n. And finally, the margin of error, it's a 95% margin of error, is equal to plus or minus 1.96 times SE. Right, so that is what we have to give when we give an estimate. Not just the point estimator, but the point estimator plus the margin of error. That gives people enough information to make sense of the point of the estimate. So it's really the kind of information that's needed, that people who really understand statistics don't just want the point estimator, they also want the margin of error. Now, because the central limit theorem also applies to discrete distributions, we can do this also for discrete distributions. So in the discrete case, we have P is the population proportion of successes our point estimator, as I mentioned in the previous lecture, is going to be P hat. It's an unbiased point estimator it's the best possible point estimator. Best unbiased, so I should say best unbiased point estimator. And again, we're going to need a standard error. So the correct standard error, it turns out in this situation, as we have discussed in Chapter 7, is the square root of PQ divided by N. The order of operations is important here. If I'm going to put brackets around this thing, I'm going to put them here. So what I do is I multiply P times Q, then I divide by N, then I take the square root. So don't misinterpret that and take the square root of PQ and then divide by N. No, you have to do the order P times Q divided by N, then take the square root. Now, the same issue with this expression as with the previous discussion. P and Q are not known to us. If P was known to us, then we wouldn't have to go through all of this anyway. But P is not known to us, so we have to estimate the standard error. And we do that by using P hat and its buddy Q hat. And instead of P and Q. So that is our approximation to the standard error, and typically in our large sample case, which if you recall is NP is greater than 5, NQ is greater than 5 is large sample for the discrete case. This formula is a good approximation to the actual value. So we can, without too much concern, just drop in what we know and can easily calculate, this guy, in place of the exact correct version, which is the previous one. All right, and again, margin of error, same formula. The margin of error in this case is plus or minus 1.96 times the SE, and that, of course, is the 95% margin of error for 95% confidence. We will discuss how to change that very soon. All right, so one thing I forgot to mention that, of course, is that in this first case, this continuous case, it's also a large sample and is greater than or equal to 30. In the second case, it is discrete. And we have, of course, the conditions, and P is greater than 5, and Q is greater than 5. Oops. And again, I don't know P, and I don't know Q, so I'm going to have to replace P with P hat and Q with Q hat. I guess there's one other little tiny thing that I didn't mention here, and that is what Q hat is. Q hat, of course, is 1 minus P hat. So P hat is the proportion of successes in the sample. Q hat is the proportion of failures in the sample. All right, so that gives us all the formulas we need to actually do some problem solving. So there are some examples in the textbook. I'll refer you to the textbook. I will try to do some examples that are from the problems at the back, so you have something a little different to look at. So let's look at hotel costs. This in my textbook is 8.20. I'll read it to you just so you can find it in your own textbook. I'm not sure what the number is in the older versions. Hotel costs. Even within a particular chain of hotels, lodging during the summer months can vary substantially depending on the type of room and the amenities offered. Suppose that we randomly select 50 billing statements from each of the computer databases of the Marriott, Westin, and Doubletree hotel chains and record the nightly room rates. And so they have some data here. I'll just copy the data. So they have the sample average. This is example 820. So there's the sample average cost of the hotel room in dollars, and there's the sample SD in dollars. So 50 billing statements. And that is greater than 30, so it's large sample. And we're going to look at the Marriott, we're going to look at the Westin, we're going to look at the Doubletree. Marriott, $150 a night with a standard deviation of $17.2. Westin is $165 per night with a standard deviation of $22.5, and Doubletree, a bargain at $125 a night with a standard deviation of 12.1. So we are just asked to find the point estimate and the margin of error for each of these different hotels. So the point estimate for Marriott do each one separately. The Marriott, the point estimate is 150. The standard error is approximately S over the square root of n, and that is 17.2 divided by the square root of 50. Let's pull out the calculator. Square root of 50 is about 7, very close to 7, but let me do a more accurate calculation here. 17.2 50 square root divide 2.4324. Okay, and finally the margin of error. That's plus or minus 1.96 times SE. Calculator says 4.77. Okay. We're going to do the same thing for the Weston. X bar is 165. Dead easy, that part of the question. The standard error, straightforward calculation, is going to be approximately 22.5 divided by the square root of 50. Need a calculator. .18 and a couple more decimals. Margin of error is plus or minus 1.96 times the standard error. It's going to be plus or minus 6.24. And finally, for DoubleTree, X bar is 125. Standard error is 12.8 divided by the square root of 50. .81. Oops. And margin of error is 1.96 times the standard error. That is 1.96 times 1.81. 3.55. All right. So next, let's graph these numbers. So I'm going to create a bar chart for the hotel price. Marriott, Westin, DoubleTree. The x-axis will go up to about, let's see what we go up to, about 150, 165. So we're going to go up to, let's go up to 175. We'll see why in a second. So let's just go up by 25, say 25, 50, 75, 100, 124. Oh, that's no good. All right, I need to give myself more space here. Let's just start over again. I like this. Eraser, yeah. Okay, let's use the whole shooting match here. So, M WD. I'm going to go 25, 50, 75, 100, 125, 150, 175, 200. So it's $200 a night. 150, 150. All right. So let's graph where the Marriott is on this chart. Marriott is 150. So we're going to put a bar up to 150. There. And Westin is 165, so we're going to put a bar going up to 165. It's about there. Look at that, it made my line nice and straight. Yeah. Okay, and finally DoubleTree, 125. Going to put a bar up to 125 for DoubleTree. All right. Now, you remember that these are just the sample, these are the sample means. So they're just estimators for the true population mean. So I can't say that the mean cost of a Marriott room is $150 a night because I've only taken a sample. But with my new technology here, the margins of error, I can give a pretty good, pretty good estimate of where the actual mean is. So remember, we're looking at plus or minus 4.77 for the margin of error. So it's about 5. I'm going to go plus or minus 5 or so. And this is very much like our bar, not bar chart, it was a box plot with whiskers. If you remember the box plot with whiskers, this is kind of the same idea. We're attaching whiskers to the bar to show that it's not a certainty that the number is actually 150, but there's some variability associated with that. And so the number could actually be in this range 150 plus 4.77 all the way down to 150 minus 4.77, and that is about 5. So it can be up to 155 or down to 145. So this tells us that we are 95% certain that average cost of a Marriott room is in the range 150 plus or minus $4.77. So when we quote this, we quote the point estimator and we quote the margin of error. To be useful, we need to put both of them. If you're a cheap newspaper like USA Today, you just give the 150. But that's not adequate if you know anything about statistics. You know that that's misleading potentially. So we have to give both pieces of information. And now we can really make a true statement. If I say the average is 150, that's almost certainly not a true statement. But if I say that there's a 95% certainty that the average cost of a Marriott room is in the range between 145 and 155, then I am making a true statement. So if I say it's 150, that's not a true statement. If I say it's in the range between 145 and 155, 95% of the time, that is a true statement. So that's important. It's very important in science for us to make true statements. The second one, how do I graph the Weston? Well, it's about plus or minus 6.24, so we're at 165. So we go up to 171. Our whisker goes up to 171, so just shy of 175. And it goes down the same distance here. Yeah. And then the same for the DoubleTree. The margin of error is 3.55. So I'm going to make my bar just a bit smaller here for the DoubleTree. Less uncertainty for DoubleTree. All right, so that's how we can graphically represent the results of our investigation using these kind of whiskers or uncertainty bars, sometimes they're called. There's different names for them. If we're not going to take the trouble to graph it, then we just give this summary here, and these three numbers that we need. These three numbers are what we need to give complete and true information in this case. 95% or whatever our confidence level is, and then 150, which is our point estimator, and then our margin of error, in this case 4.77. So you need to quote three numbers when you give an answer to this type of question. All right, so that is a complete question. One other thing that I would like to draw your attention to is that we are not given raw data for this question. This data has all been processed already. Right, so somebody has taken 50 numbers, added them up, found the average, and found the average to be 150. And somebody has done the same thing here. So right now, at this point, we've done 50 arithmetical operations for each. So that's 150 operations have been done to calculate the means. To calculate the standard deviations is even more, roughly double that. So probably 100 different operations to calculate this guy, 100 for this one, 100 for this one. So altogether that's 450 calculations or simple arithmetic operations, additions, squarings, divisions, square roots, whatever, have been done, 450 operations. So I would never ask you for this type of question to actually process the data. There's just too much. It's not really a kind of a good question, because you're just doing arithmetic for 15 minutes or half an hour. So the data will be presented to you in summarized form, in processed form. Already somebody has calculated for you what the mean is, what the standard deviation is. There are other cases where you have to do it by hand, but in this type of question, in this chapter, for large sample, there's just too much arithmetic. So you will almost always see the data pre-processed for you. But when you do this in your work life, when you start taking statistics and applying it in your real life or in your other classes, the data that you're going to work with will not be pre-processed. You'll have raw data. You will have to calculate these averages. You will have to calculate these standard deviations. And if you're lucky, you'll be able to use a computer or a spreadsheet to do that. But you also may end up doing that by hand sometimes too, and that's part of doing statistics. You have to know how to do it by hand, even if most of the time you have a computer that can do it for you. All right, so that's just a little kind of an aside, something I wanted to point out to you, that we are using data that's been processed. The raw data is 150 different measurements that have been taken for this investigation. But we are in the fortunate position of jumping in near the end of the processing of all of that. All right, so that is how we can do a question about margin of error. and estimations for a continuous example. Now let me see. I thought I had picked a good one, but let's do mosaic or melting pot. So this is 823 in the textbook. This one is different because it is discrete. And in this case, we're talking about population proportion. So P is the parameter of interest that we would like to learn about. All right, so I will read this question to you in case you don't have access to it. The concept of the mosaic, where cultural differences within society are deemed valuable and regarded as something that should be preserved, is often used to distinguish Canada from the United States. Based on the online survey of a representative national sample of 1,006 Canadian adults, let's just write down. Use letters to represent these. It'll help to clear our mind and keep focused. So N is 1,006 Canadian adults. 54% believe Canada should be a melting pot, while 33% of Canadians endorse the concept of the mosaic. The melting pot is particularly attractive for Quebecers, 64% Albertans, 60% in respondents over the age of 55. All right, there's a whole bunch of numbers floating around here, so we'll have to read further into the question to find out what's really relevant. The mosaic gets its best marks among British Columbians, 42%, and respondents aged 18 to 34. Based on the survey result, give a point estimate P for those Canadian adults who believe Canada should be a melting pot. Right, well, that's easy. It's given to us in the question, so we have 54%. That's a decimal. My calculator doesn't like percents. So 54% believe Canada should be a melting pot. So that is the answer to part A. Part B is to find the margin of error of your point estimate. All right, so this, in order to calculate this, we first need to calculate the standard error. And the standard error is approximately P hat Q hat over N, and then I take the square root of the whole shebang. Right, so the correct value uses P and Q, but we don't have access to P and Q, so we're going to have to use P hat and Q hat instead. P hat is 0.54, so Q hat is 1 minus 0.54, which is 0.46. And that means that the standard error is the square root of 0.54 times 0.46 divided by 1,006. And then you take the square root. Here I'm pulling out my calculator. 0.54 times 0.46 divide by 1,006. And then I take the square root and I get 0.0157. Margin of error is plus or minus 1.96 times the SE. So I multiply that number in my calculator times 1.96, and I get 0.03. So 3% margin of error. Right, so in summary, our point estimator is 54% of Canadians believe Canada should be a melting pot, and 3% margin of error to that number. And 3% is actually quite typical for kind of a telephone survey. If you look in the Globe and Mail, it's better than USA Today. So Globe and Mail will give margins of error. And the way, well, one way we could write it is like this: 95% confident that the proportion of Canadians who believe Canada should be a melting pot is 54% with a margin of error of 3%. So that would be one way to write it. Another way, which I find helpful to think about it, is that we're 95% confident that the proportion of Canadians who believe Canada should be a melting pot is between 51% and 57%. So either way, the latter is less technical sounding, but maybe it involves a little more calculation, so either way is fine. One thing to note about this is that we're 95% confident that the number is over 50%, so that is something else that we could say. We're 95% confident that the proportion of Canadians who believe Canada should be a melting pot is greater than 50%. So that's something else we could conclude from this. We cannot dispense with this confidence level, though. We have to quote it. It's very important. Otherwise, we are not making true statements. If we just say that the proportion of Canadians who believe Canada should be a melting pot is between 51% and 57%, that denies the possibility that we may have just taken a sample which was a bit off. But when we're sampling, we always have to face the possibility that our samples may not be representative. There's a small chance that the sample is not representative, a 5% chance that the sample is not representative. So we have to be honest about that whenever we give these statistical results. And now again, here I imagine some of you are saying, well, what if I really want to be 100% sure? Well, you go and survey every Canadian then. Whatever it is, it's 30 million people. So you go out there and ask 30 million people what they think. We got a 95% confidence by surveying only 1,000 people. So, we've achieved a fairly high degree of certainty, an acceptably high degree of certainty with a reasonably small expense. Compare that to the cost of 30 million, which would be 30,000 times larger. So if it cost us $100 to run the survey, it would cost, to scale it up and ask every Canadian would cost 30,000 times 100, which is 3 million. $3 million for the survey. We can't afford that. So here we are. We have to be happy with 95% confidence, but we also have to be honest about it. We have to quote it. And a good newspaper like the Globe and Mail will say we are 95% confident, or instead of saying 95% confident, they will say sometimes 19 times out of 20. And you'll see that in many Globe and Mail articles. The survey is considered to be accurate within 3%, 19 times out of 20 is how the Globe and Mail will quote that. All right, so that is the end of 8.2, 8.3. We've done a couple of problems from 8.3, so we'll stop now and give you a chance to clear your head, and I will come back and start to do the other sections from 8.4